Welcome students once again into the class of number theory, and in this video we will discuss more problems related to Mobius function, Mobius inversion formula, multiplicative functions, Euler's tangent function, etc. So let us see what the problems we are going to discuss in this video. The first problem I am going to take in this video. So please write down the statement first so that you can understand the proof easily. Let capital F be a multiplicative function and small f be an arithmetic function such that capital Fn is equal to sigma small fd, where d divides n, then show that small f is also multiplicative. What we are given in this video is this, that capital Fn is equal to small sigma small fd, where d divides n, and we are also given that capital F is a multiplicative function. This is also given, and what we are to show that small f is also a multiplicative function, where small f is an arithmetic function satisfying this identity. So let us see how to prove it, how to find the solution, how to arrive at this conclusion that small f is also a multiplicative function. We are given that capital Fn is equal to sigma small fd, d divides n. Using Mobius inversion formula, we can find the value of small f in terms of capital F, and that value will be given by small fn is equal to sigma mu d capital F n by d, where d divides n. If capital F is this, then small f will be this, by using Mobius inversion formula. And now we have to show that this small f is a multiplicative function. For that, what we have to do, we will take two natural numbers m and n such that their GCD is 1, and then we will show that small fmn is equal to small fm small fn. So let mn be natural numbers such that GCD of m and n is 1. So this is the step from where we have to start. Now fmn is equal to, you have just replaced n by fmn. So what you have to do, you replace this n and this n by mn. So what you will get, sigma d divides mn mu d capital F mn by d. In a previous video, you have seen that if d divides mn and GCD of m and n is 1, then d is of the form d1 d2, where d1 is a divisor of m, d2 is a divisor of n, and GCD of d1 and d2 is also 1. So therefore d is of the form d1 d2, where d1 divides m, d2 divides n, and GCD of d1 and d2 is 1. This we have seen in the previous video. This I am going to use here now. So it is equal to sigma, this d divided by mn, I am replacing it by d1 divides m and d2 divides n, comma, separated by a comma. This mu d can be replaced by d1 d2. So this is mu d1 d2 into f of mn divided by, once again, this d is d1 d2. So this concept I have used, I am going to rub it from here now because I have used it right now. Okay, now this mu This Mobius function is a multiplicative function, and GCD of d1 and d2 is 1. So mu of d1 d2 can be separated as mu d1 mu d2. So this is mu d1 mu d2. Also this f is a multiplicative function, and f of m upon d1 and n upon d2 are also co-prime to each other, so this can also be separated. So you can have here f of m upon d1, f of n upon d2. Now you separate, you make pair of this with this and pair of this with this. So what you will get? You will get sigma mu d1 f m upon d1, where d1 divides m, into sigma, the rest of the terms are mu d2 f n upon d2, where d2 divides n. Compare this with this. Sigma d divides n, here d1 divides m, mu d, okay, mu d1, fn by d, fm by d1. Okay, so what the first term is, this is nothing but this is your fm. And similarly, the second summation form is fn. So your fmn is equal to fm into fn, and that means your small f function is also a multiplicative function, because you have taken GCD of mn to be 1 and you have proved that fmn is equal to fn. So this was another interesting problem based on Mobius inversion formula, multiplicative functions and divisors of natural number m and n. So another problem I am going to take in this video. Note down the problem first so that we may move on to the solution later on. If n is in canonical form p1 alpha 1, p2 alpha 2 and so on, pk alpha k, then sigma mu d upon d is equal to 1 minus 1 upon p1 into 1 minus 1 upon p2 and so on into 1 minus 1 upon pk. This result we are going to prove now. Okay, let us move on to the solution. Before moving on to the solution, in a previous video we have proved this result, that phi n is equal to sigma d divides n mu d into n by d. This result we have already proved in a previous video. You can check, you can see previous video for the verification. This we have proved. Now the right hand side, here what the variable is, that d, because d divides n. You change d, the term will be changed, but n will be fixed. Whatever is fixed can be taken out of the summation. So I am taking this n out. What I will get, phi n is equal to n sigma mu d upon d, d divides n. From here, what is the value of this term? Take n to the denominator on the other side. So sigma mu d upon d, where d divides n, is equal to 1 upon n into phi n. N is your number this. N is your number this. P1 alpha 1, P2 alpha 2 and so on, Pk alpha k. Once again, in a previous video, go to the previous videos and see that we have proved that this phi n is equal to n times 1 minus 1 upon P1 into 1 minus 1 upon P2 into and so on 1 minus 1 upon Pk. This result we have proved in a previous video. This n will be cancelled, and what you will be left with, sigma mu d upon d, where d divides n, is equal to 1 minus P1 into 1 minus 1 upon P2 into and so on 1 minus 1 upon Pk, and that is the required result to be proved in this problem. So in this problem, what we have done, we have used two results proved in previous videos. So this is another very interesting problem, may be asked in your final examinations and is also useful for the future problems what we are going to face in future. So this problem was being proved, and now we are moving on to another problem. So the next problem what I am going to take is that prove that sigma mod of mu d, where d divides n, is equal to 2 power k, where what is k? Where k is the number of distinct prime factors of n. That means when you will expand n using fundamental theorem of arithmetic, how many prime numbers will be there? That will be k. So what we have given, this k is the number of distinct prime factors of n. It indicates that your n is of the type p1 alpha 1, p2 alpha 2, and so on, pk alpha k. So there are k distinct primes in the factorization of n. Another thing, that this mu d, I am defining a function fn. Let fn be this function sigma mod mu d, where d divides n. Note that this mu d, the Mobius function, is a multiplicative function. So mod mu d is also a multiplicative function. So their summation is also a multiplicative function. That means this capital Fn is a multiplicative function. Then this capital Fn is a multiplicative function. This is a multiplicative function. Let us see what is f of p1 power alpha 1. Let us see what is f of p1 power alpha 1. So f of p1 power alpha 1 means here you will have p1 power alpha 1, rest will be the same. So you will get sigma mod mu d, where d divides p1 power alpha 1. So d is a divisor of p1 power alpha 1. And what are the divisors of p1 power alpha 1? They are 1, p1, p1 square, p1 cube, p1 power 4, and so on up to p1 power alpha 1. Put these values one by one here, take mod and then sum. So you will get mod of mu 1 plus mod of mu p1 plus mod of mu p1 square plus and so on mod of mu p1 power alpha 1. You will get this. Okay, what is mu 1? By definition of Mobius function, mu 1 is 1, so mod of 1 is 1. So the first term is going to be 1. What is mu p1? This number p1 has one prime factor. By definition of Mobius function, the value will be minus 1 raised to the power 1, and minus 1 raised to the power 1 is minus 1, so you will put here minus 1, but the mod is there. So mod of minus 1 will again become 1. And for the rest of the values, here p1 square is not square free because p1 square divides it, perfect square divides it, so the value of this term will become 0 and so on. Rest of all the terms will be equal to 0. So it is plus 0, plus 0, plus and plus 0. So it is equal to 2. What the interesting fact you have seen that p1 alpha 1 is equal to 2 and it is not depending upon p1 or alpha 1. Whatever is the value of p1, whatever is the value of alpha 1, the value of f of p1 alpha 1 is coming out to be 2. Okay, so this value is coming out to be 2. I am writing it over here and I am rubbing the rest of the part because we have already proved it. So it is clear that if you take f p2 alpha 2, it is again 2. If you take f p3 alpha 3, it is again 2 and so on. Now look at, you want this. You want this sigma, sorry, mod is inside, sigma mod mu d, where d divides n. This is equal to fn. And fn, what is your n? Your n is this. So it is f of p1 alpha 1, p2 alpha 2 and so on, pk alpha k. Now this p1 alpha 1, p2 alpha 2, pk alpha k, they are all co-prime pairwise, relatively prime pairwise because they are all prime numbers. And this function f is multiplicative, so it can be separated. It can be written as f of p1 alpha 1 into f of p2 alpha 2 and so on, f of pk alpha k. So we have used the property of multiplicativity of the function capital F. Now what is f of p1 alpha 1? It is 2 into what is f of p2 alpha 2? It is again 2 and so on. How many times? K times. So it is k times. And 2 multiplied by 2 multiplied by 2 multiplied by 2 k times is clearly 2 raised to the power k. So we have shown that sigma mod mu d, where d divides n, is equal to 2 power k, and that is the required result to be proved. So this problem is again being solved, is being proved, and more problems we will discuss in this video. Maybe 2, maybe 3 more problems I will discuss, and then I'll leave this video, I'll close this video, and in the next video I'll try to take greatest integer function, de Polignac formula, and so on. But before that, in this video I'll take more problems based on Mobius inversion formula. The next problem I'm going to take is, write down the problem, write down the statement. If n is p1 alpha 1, p2 alpha 2, pk alpha k, as in the canonical form using the fundamental theorem of arithmetic, then sigma mu a dA, where a divides n, is equal to minus 1 raised to the power r. Here I have taken a as a divisor of n, not d, because I am already using the function d here, the number of divisors of a or the number of divisors of n. This function is already being used, so by I am changing the symbol here, I have used a here, a divides n. And the proof is very much similar to the previous problem. So I'll use the same way that I've used in the previous problem to prove this question, to solve this question, and let us see how it is being solved. N is given to be this. This we are to prove. We will consider this to be capital Fn. Let capital Fn be sigma mu a dA, where a divides n. Once again, this mu is Mobius function. It is multiplicative. This dn, we have already shown that it is also multiplicative, and product of two multiplicative functions is a multiplicative function, and their sum is also a multiplicative function. That means this capital Fn is a multiplicative function. So then this capital Fn is a multiplicative function. Now once again, in the same way, in the same fashion, on the same lines which we have used in the previous question, I'll try to find the value of f p1 alpha 1. So what is f of p1 alpha 1? In this definition, here you have taken p1 alpha 1, so just replace this n by p1 alpha 1. So it is sigma mu a dA, where a divides p1 power alpha 1. So you just take one by one the values of a as the divisors of p1 power alpha 1 and then take their sum. And what are the divisors of p1 power alpha 1? Once again, the divisors of p1 power alpha 1 are 1, p1, p1 square, p1 cube, and so on up to p1 power alpha 1. So I'll put these values one by one in place of a here, and then I'll take the sum. So what we will get? So first replace this a by the first divisor 1. So it is mu 1 d1 plus mu p1 dp1 plus mu p1 square dp1 square plus, and so on. In the last you will get mu p1 alpha 1 dp1 alpha 1. Okay, mu 1. By definition of the Mobius function, the value of mu 1 is 1. So this is 1 multiplied by d1. d1 is the number of divisors of 1. So number of divisors of 1 is again 1. So it is 1 plus mu of p1. This is containing only one prime factor, p1. So the value will be minus 1 power 1. So it is minus 1 raised to the power 1 multiplied by dp1. dp1. That means number of divisors of p1. How many divisors of p1 are there? 2. 1 and p1. So dp1 is 2. Plus rest of all the terms will become 0. Because p1 square is not square free. And if a number is not square free, its mu is 0. p1 cube is not square free because it is divisible by p1 square. So its value is again 0, and so on. Rest of all the terms will become 0. And you will be left with this 1, and this is minus 2, so minus 1. Once again, we have seen that this f p1 alpha 1 is coming out to be minus 1. It is not depending upon p1, it is not depending upon alpha 1. That means f p2 alpha 2 is also minus 1, f p3 alpha 3 is also minus 1, and so on. So I am rubbing all this portion and just I am writing here that f pi alpha I is equal to minus 1 for every I is equal to 1, 2, 3, and so on to k. This is f of pi alpha I. And now move on to the main thing. You have to find the value of this. So start from here. Sigma mu a dA, where a divides n, is equal to, we have supposed that it is equal to fn. So it is fn. And now substitute the value of n, this value. So you will get f of p1 alpha 1, p2 alpha 2, and so on, pk alpha k. Once again, these p1 alpha 1, p2 alpha 2, pk alpha k, they are relatively prime in pairs. And the function f is multiplicative, so they can be separated as f of p1 alpha 1, f of p2 alpha 2, and so on, f of pk alpha k. But each of these one is equal to minus 1. So we will get minus 1 minus into minus 1 into minus 1. How many times? K times. So it is equal to minus 1 power k. So we have proved the result. Sorry, I have written here r. It should be k. It should be k because the number of prime factors is k. So it should be k here. And we have proved that sigma mu ADA, where a divides n, is equal to minus 1 raised to the power k. So this problem also we have proved. One or two more problems I'll take before ending this video, because I'll try to finish the topic of Mobius functions in this video. I want to start with greatest integer functions in the next video. So I'm going to finish the Mobius functions and its applications, or the main results or the main theorems here. The next problem I'm going to take, write down the statement, prove that sigma summation sigma d1, this is the sigma of summation, this is the sigma function, sum of divisors of d1, sigma d1 phi n upon d1, where d1 divides n. Why I am using d1 here? Because once again I will use d for the function number of divisors of n, so it is equal to n dn. Here this d stands for the function number of divisors of n. We have to prove this result, and the line of proof is almost the same as we have used in the previous two questions, but not exactly same. It is almost same. At some stage we will have to use our brain, we will have to use some typical tips to reach the conclusion. So let us see how to prove it, how to find the solution. Once again, let this be your Fn. Fn is equal to sigma d1 phi n upon d1, where d1 divides n, and let n be p1 alpha 1, p2 alpha 2, and so on, pk alpha k. This sigma, we have shown that it is a multiplicative function. This phi, the Euler-Stoichhian function, is already a multiplicative function. Their product is a multiplicative function. Summation is a multiplicative function. So that means this capital Fn is a multiplicative function. Is a multiplicative function. This is a multiplicative function. As in the previous two questions, the same lines I'll follow. I'll start with f of p1 alpha 1. What is f of p1 alpha 1? F of p1 alpha 1. Replace this n and this n by p1 alpha 1. So what you are going to get? Sigma d1 phi p1 alpha 1 divided by d1, where d1 divides p1 alpha 1. So what are the divisors of p1 alpha 1? They are same. 1, p1, p1 square, p1 cube, and so on. So substitute d1 is equal to 1, then d1 is equal to p1, then p1 square, then p1 cube, and so on in both these places, and then add. So what you will get? The first term. First put d1 is equal to 1. So it is sigma 1 and phi. When you will put 1 here, p1 alpha 1 over 1 will be p1 alpha 1 plus, then put d1 is equal to p1. So it is sigma p1 and it is phi. Here you put d1 is equal to p1. p1 alpha 1 upon p1 will become p1 alpha 1 minus 1 plus sigma p1 square phi p1 raised to the power alpha 1 minus 2 plus, and so on. In the last you will get sigma p1 alpha 1 into phi 1. And now substitute their values. Sigma 1, sum of divisors of 1. That is, there is only one divisor 1 and the sum is itself 1. So it is 1. And phi of p1 alpha 1, we have already proved that it is equal to p1 power alpha 1 minus p1 raised to the power alpha 1 minus 1 plus sigma p1, sum of divisors of p1. There are two divisors, p1 and 1, and their sum is 1 plus p1 into phi of p1 alpha 1 minus 1 is p1 alpha 1 minus 1 minus p1 alpha 1 minus 2, and so on and so on. And when you will simplify it by opening brackets, I'm not going to open the brackets, I'm telling you when you will open the brackets, you will solve these, what you are going to get, you will get k plus 1 times p power k. You will get this. When you solve these brackets, you will get k plus 1 p power k. This k plus 1 is the number of divisors of p power k. So you can write this p power k first, and this k plus 1 you can write it as d of p power k, because number of divisors of p power k, how many divisors are there? These are 1, p1, p1 square, p1 cube, p1 4 and so on, p1 power k, that means k plus 1. So I have replaced this k plus 1 by dpk. Here I have used a little bit trick to solve this question. Okay, so I'm going to write the result directly. This is a little bit problem I think is there, because k plus 1 pk, I'm using p1 alpha 1, so it is p1 power alpha 1 here, and here again p1 power alpha 1, and this simplifies sum, you will get alpha 1 plus 1 p1 alpha 1. This term, actually I have solved it in another way by taking alpha 1 is equal to k and p1 as p. But you are having here p1 and alpha 1, so when you solve it, you will get this alpha 1 plus 1 into p1 alpha 1, which is equal to p1 alpha 1 dp1 alpha 1. So I am writing this value here. I am deleting all the rest of the terms. What the value we have obtained here is p1 alpha 1 into d of p1 alpha 1. This I have obtained, and now I will use this value to prove the required result. The required result, once again I am starting from here. This is sigma d1 phi n upon d1, where d1 divides n is equal to fn, and fn, what is your n? Your n is this p1 alpha 1, p2 alpha 2 and so on. So it is p1 alpha 1, p2 alpha 2 and so on, pk alpha k. But what is your f? It is a multiplicative function. You can separate it. You will get f of p1 alpha 1, f of p2 alpha 2 and so on, f of pk alpha k. What is f of p1 alpha 1? F of p1 alpha 1 is your p1 alpha 1 into d of p1 alpha 1. Similarly, f of p2 alpha 2, it is p2 alpha 2 d of p2 alpha 2 and so on. In the last you will get pk alpha k into d of pk alpha k. It is power pk alpha k. Now this p1 alpha 1 into p2 alpha 2 and so on, pk alpha k, this is nothing but n. So you will get n here, and dp1 alpha 1, dp2 alpha 2, dpk alpha k, and d, the function number of divisors of n is also a multiplicative function. So these will be combined to give you d of p1 alpha 1, p2 alpha 2 and so on, pk alpha k. And what is the p1 alpha 1, p2 alpha 2 and pk alpha k? This is nothing but n. So you will get n dn. So you have proved that summation sigma d1 phi n by d1, where d1 divides n, is equal to n dn, and that was the required result to be proved. So this result also we have proved. Another important result I am going to take in this video, because again and again I am telling you, I am trying to finish the topic of Mobius function at least here, so that in the next video I may take the greatest integer function, its applications, its theorems, its lemmas, and then the chapter arithmetic functions will be closed. So maybe the next video, the last video of this chapter, arithmetic functions. This may be the second last. I am trying. So let us have one more problem. Let us have one more problem, that is, prove that sigma d vary from 1 to n phi d greatest integer function n by d is equal to n into n plus 1 upon 2. This we are going to prove now. So let us see how to prove this question, this function. Solution. I'm moving on to the solution now. Let this expression be denoted by some function fn. So let fn be sigma d vary from 1 to n phi d greatest integer function n by d. If it is so, what is the value of fn minus 1? Just replace this n by n minus 1 in these both places. So you will get sigma d vary from 1 to n minus 1 phi d greatest integer n minus 1 upon d. Now I am adding one term here. That is phi n greatest integer function n minus 1 upon n. I can add. Why? Because n minus 1 is less than n. And if n minus 1 is less than n, then n minus 1 upon n is a fraction. And fraction means 0 point something. If a quantity is 0 point something, then its greatest integer value will be 0. So this is 0, and 0 multiplied by anything is 0. So I have done nothing, but I have added 0. So 0 can be added anywhere without changing the value. So I just added a 0 here. But by adding this term, what happened? You are having this sum up to n minus 1. And if you put d is equal to n here, it will become phi n minus 1 upon n box, and this is in fact this term. That means this term corresponding to this sum for the value n. So this the sum becomes sigma d varies from 1 to n now phi d n minus 1 upon d. This term is included in this, and it makes the sum up to n, because the last value n will give you this term. Okay, so this is your fn minus 1. Now from this fn you subtract this fn minus 1. fn minus 1. So sigma d vary from 1 to n both places. So sigma d vary from 1 to n. Phi d is here, so phi d can be taken as common, and in the bracket you will get this greatest integer function minus this. So you will get box n by d minus box n minus 1 d. You will get this now. Okay, here d is varying from 1 to n. Suppose your n is 10, then value of d is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Out of these values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, some of the values divide n, some of the value does not divide n. So I can break this sum into two parts. One part where d divides n, the other part where d does not divide n. So I'm breaking it sigma phi d n by d minus n minus 1 by d when d divides n plus sigma phi d greatest integer n by d minus n minus 1 by d where d does not divide n. So I've broken this sum into two parts. In one part those d which divide n, in the other part those d which does not divide n. When d divides n, so n upon d will be a whole number and it will be a little bit small, maybe some fraction small. So this value minus this value will become 1, because if it is suppose k, then it is k minus 1. So if it is k and if it is k minus 1, so k minus bracket opening k minus k plus 1 will become 1. So this bracket, this value will become 1 in this case. So you will get sigma phi d into 1 when d divides n. It is the first part. And when it is the second part, then n upon d and n minus 1 upon d will have same integral part. So their value will be same. If their values will be same, the portion will be 0. This is 0. Phi d multiplied by n is 0 is a 0. So the second part will give you sigma phi d into 0 where d does not divide n. So that means 0 into anything is 0 and their summation is 0. So this term can be deleted. So this term is being deleted. And phi d into 1 is again phi d. So this 1 can also be deleted. So you get sigma phi d where d divides n. And this sigma phi d divides n, you have already proved that it is equal to n in a previous video. In a previous video we have shown that sigma phi d, if d divides n, is equal to n. Go to the previous videos and see the result again, see the proof. So what you have proved, that fn minus 1 is equal to n. This we have proved. So I am rubbing this portion now, because what the result I required, I have obtained the result that this fn minus 1 is equal to n. Okay, now put the values of n to be 1, 2, 3, 4, 5 and so on up to n. If you will put 2 here, you will get f2 minus f1 is equal to 2. If you will put n to be 3, f3 minus f2 is equal to 3. Similarly, f4 minus f3 is equal to 4 and so on. fn minus fn minus 1 is equal to n. And now add these all equations. When you will add all these, f2 will be cancelled, f3 will be cancelled, f4 will be cancelled, similarly fn minus 1 will be cancelled. On the left hand side you will be left with fn minus f1. On the right side you will get 2 plus 3 plus 4 plus and so on up to n. So I am rubbing these portion once again, because now no more I will need this portion. f1. What is f1? Put n to be equal to 1 here. So it is d vary from 1 to 1, that means only 1. Phi 1, 1 upon 1, so it will become totally 1. So the value of f1 will be equal to 1. And now this minus 1, take it to the other side. So minus 1 going to the other side will become plus 1. So you will get fn is equal to 1 plus this. So it is 1 plus 2 plus 3 plus 4 plus up to n. And you know very well that it is equal to n into n plus 1 by 2. And what is your fn? Your fn is sigma phi d, greatest integer n by d, where d varies from 1 to n, and this is the required result to be proved. So this result again we have proved. So we have done a lot of questions, a lot of problems related to Mobius function, multiplicative functions, Euler-Stoichhian function and their applications. So I am going to stop this topic here. In the next video I'll start with greatest integer function. I'll take de Polignac formula and their applications. Till then, thank you once again.